Wow. Hey guys, how are you? Welcome. This is going to be a fun night, I hope. We are actually doing something a little different tonight. We're going to be streaming if the winds calm down out there. But check this out. This is a fully processed hamburger galaxy from the last stream, if you recall. And I figured, hey, why not? Let me show you how we do this stuff. So this is sort of a behind the scenes. And I also want to show you some other things as well, which we'll get to in a little while. But I'm hopeful that you guys will enjoy this. I'm sure you will, because you seem to enjoy almost everything that we do here, and I'm happy about that. So I want to start with just saying hello to everybody. I like to see that we have Sally Forth was #1 in the chat. Nice to see you. Lori at LDP. Star Panda's with us. Corticopia. How are you, Courtney? And we have Tim Kiefer with us. Sharon and Katie. Hi, Sharon. How are you doing? Down in Texas from Houston. C&D Boy. That's Bob. He's with us. Daisy and Zoe Amethyst. Good to see you. Donald Kunzer. And that's pretty much it for now. And we will see if we get some more people joining. Well, we do have Weather is Crazy. How you doing, man? Nice to see you. Karen Belmont's joining us. It takes a little time. And we have Nicole. How you doing, Nicole? Nice to see you as well. And so we'll just wait and see how it goes. I actually got a nice email today from AJ at Y-Files. He said that, people want to see me come back on, which is really heartening. I really enjoyed that. I was really warmed by that. And he offered, to, talk to me or do anything if he wanted to talk. So that was pretty cool. Nice guy. AJ is really one of those genius level guys that it's so refreshing to be able to talk to someone and know that he is someone that will ask all the right questions if he doesn't understand something, and not just say, oh, okay, and then just walk away saying, I have no idea what he said. That happens all the time, right? But I guess if I have a superpower, I'm kind of embarrassed to say it that way, it's that I can take complex stuff and make it understandable, and that's kind of cool. That's really cool, and so I like doing that. I like spending time making sure that people understand what it is that I'm saying. Very important. So welcome everybody, and we've got more people coming in. John Proctor's with us. Hey, John. Good to see you, man. Haven't seen you for a while, except I think you were in the last stream for a few minutes. Nice to see you. And we have Davey. How you doing, Davey? What's happening? Or is that Davey in Bangor, Maine? Okay, cool. Nice to see you again. So we'll let the chat fill up with people, but I just wanted to show you what processing gets you. When we first downloaded this, it actually was. It had some noise. It was kind of noisy. All right. And we downloaded 2 files, if you recall. When we saved one, it became what's called a FITS file, F-I-T-S. That's an astronomical format. It's actually looks very unimpressive when you look at it, because you're not seeing all the hidden data. Now, you may remember in some of the streams, and for those that don't recall, I will explain, that I mentioned how the camera has a very wide depth of data that it can capture. It can capture very, very subtle, small, very faint data, okay, and also very bright data. And you can shuttle between the two ends and get the bright areas toned down so you can see the detail in them, and the dim areas, you can have them brightened out so large that you can see or so bright that you can actually see the detail hiding in the dimmest parts. Okay, that's called dynamic range. And so here we are. This is Photoshop. It's my tool for doing the processing. This galaxy is a perfect example of dynamic range, okay, on steroids. Because if we take a look, okay, at this galaxy, you'll see it's got these beautiful dark clouds of dust in here, and you'll notice that you can see detail in them. Now this is interesting, okay, and we're gonna do this from scratch with another galaxy that we did, okay. And you'll notice also that there's a red color in here. This is a galaxy that is doing star formation, and the star formation going on in this galaxy is such that it's actually, you got a lot of hydrogen emission nebulae in there. And remember, we talked about in the universe, we have a bunch of basic colors. We have red for hydrogen emission right here. So when the hydrogen atom, which has one electron, loses that electron to UV radiation coming from a hot star cluster nearby, the electron, when it bounces back into the atom, gives off a particular color light. And in hydrogen's case, it's predominantly this red little color we see right there. And so with oxygen, we see another thing happen. We see oxygen when it gives off light as the electrons too come back into the oxygen atom, because two of them get ionized for this. We get a greenish blue light. We call it teal, right? And so that light is very, very characteristic in the universe too. So we have red and we have this teal. Then we have this overall blue color here. See, this sort of blue, and it kind of winds down here. This blue these are areas where there's young hot stars that have formed in this galaxy, and these particular stars are so hot and young, okay, that they cast a very, very blue light. All right, so we have red, we have teal, we have blue. Right, then in the dark, hiding in the dark, we have all of this dust. And the startup song from our album Rising, which you heard at the very beginning, is called, Life Began in the Dark. And this is a very appropriate image for that song, because this dark dust is where all the building blocks of life get manufactured in the universe, in a galaxy. Because that dust is the remnant of supernovas, it's the remnant of red giant stars that slough off their outer layers and make molecules of dust. They're so large in the outer regions that they give off all this dust. And that dust is something that ends up capturing other particles, other elements, and molecules, and you get ice covering this dust. So you have these pockets of little tiny bit dust, tiny, tiny interstellar dust out in space by the umpteen trillions upon trillions upon trillions. It can't even say. It probably approaches one Google. Remember the Google? Okay. And so in terms of the amount of dust. And so that said, all this stuff that we see here, okay, that we see in this region here, this stuff is literally creating the building blocks of life. And so if you have this galaxy filled with all this material, eventually other stars are going to pass by, because all the stars go around the center of this galaxy. Now, albeit this galaxy looks a little strange, doesn't it? It has this little appendages out here and even further. Then it has this one out here. It looks kind of misshapen. It looks like its central disk that we tend to see on a galaxy is been dragged down. And that's a very, very good observation, because it has. See, down below this galaxy are two others, because this galaxy is known as one of the Leo triplet in the Leo constellation. And this particular galaxy is one that has a interaction with those other two galaxies. And those other two galaxies are tugging at it and pulling at it. They're all kind of relatively close to each other in space, and they've passed each other. And as they've done so, the galaxy below has kind of torn some of its dust off and pulled it down. Okay, and the dust is more massive than the gas, so it's going to react to gravity, have its own gravity, much that's higher than just the plain gas. So the dust is going to get pulled down, and that's kind of what we see here. And these stars here are all here in our foreground. They're in our foreground galaxy. That galaxy is way, way out there, way, 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 many, many light years away, several tens of millions of light years away, in fact. So actually, when you look at this galaxy, what you're seeing is a galaxy that is, the light coming to you left it millions of years ago. One of the talks I'll be doing out in Contact in the Desert out in Indian Wells, which is near Palm Springs, in a month or so, is going to talk about the timeline of light reaching us from these distant objects and what was happening on Earth at the time. Now that's kind of cool, because that way you actually have a perspective about how the Earth was developing. And for one of them, we're going to see light that came from a galaxy so far away that the Earth wasn't even here yet. In fact, our galaxy hadn't even formed yet when that light left it. So that's pretty cool. So if you're planning on going to Contact in the Desert, look, I think it might be worth your while to go to that particular talk that I give, because that's going to be a neat one. All right. And I have 2 more lectures, and I'm running 2 Skywatches with Ben Hansen, a good friend of mine. And so we're going to end up talking to thousands of people before the week is done out there. So this is cool. So this particular galaxy then is one that actually has lots of this detail. There's those red hydrogen regions I was talking about. Now, do those look this way right now at this exact moment? Maybe not. Because they've had several tens of millions of years, I think like 40-something million years of time to change. So I don't know how they look now. All right, but this is neat how when you look at the dust here, you can actually see how it's being pulled down here. And that's what's really neat. So gravity has a way, it's slow, but gravity has a way of interacting with everything, you know? And of course, Tiffany Echo, who is hiding her name by calling herself Star Panda in the chat, says something that's a mainstay of what we have done in the past, and that is we offer giveaways. We do telescope and binocular giveaways on our channel with Skyter Livestream. And so that will be starting up again, and we're going to be doing some out in Indian Wells at Contact in the Desert as well. And I think, if I don't miss my guess, for several of my lectures out there, we're going to have a drawing, and people can put in a ticket. They all get one when they walk in the door, and we do a raffle at the end of the talk, and you get equipment. And that equipment can be given to you pretty quickly, or it gets mailed to you. Depends what it is. If it's a telescope, well, no. You have to get it mailed to you. But if it's a pair of binoculars, I'm not sure. Star Panda, let me know if I'm speaking out of turn, and that'd be very helpful, So we have Donald King is in the chat. Thank you for adding that the Leo triplets approximately 35 million light years away. I think the Hamburger galaxy here is farther than the other 2, is it not? I'm trying to remember. And Cornucopia is going to be happy with me because one of the favorite objects that she told me about is something we're going to actually do an image processing on from the very beginning, so you can watch what happens and how we pull this data out of our imagery. And Karen Belmont says, I love my binoculars, and that's because she won binoculars from us. All right, so see, we touch everybody if we can. We love giving away equipment. We love bringing people into our discussion, and this is how we do it. Now, to tell you something else really quick, I'm going to bring up one other thing. Okay, now, this is our Benson view right now. Notice it's a beautiful blue sky. And you might say, hey, we can turn on the telescope and use the telescope. Yeah, but the problem is the winds are almost 30 miles an hour out there right now. Now, we'll keep looking. I'm going to refresh here and get a view of the all sky. Sun is setting. We do have some light clouds a little bit. That's a jet contrail. But this is pretty much clear tonight out there. And we're going to do our best to see if we can bring that out for you to see. And then you'll actually see the whole startup process for the telescope too, which is kind of neat. And Tiffany, who is Star Panda, says, I'll have the binoculars with us, but yes, if it's a telescope, it'll be shipped, so you're not carrying a large item around. That's correct. It's a giant box. It's a fun starter telescope from Celestron, and the binoculars are really fun binoculars from Celestron as well. And so, we're trying our best, to bring everybody into the conversation in astronomy. When I got my degree in astronomy, I never dreamed that I would be able to take pictures like this of objects that are this so far away, millions of light years away. But here it is, right in front of us, and I'm like, wow, I can't believe how this went. the length of time, everything that's happened over the course of my life, through all the weird things that have happened to me, from weird encounters with things I don't understand to medical issues that I unfortunately did understand. I've sort of come out doing okay, and all I kept thinking of the whole time. I'm going to share this with you. About 11 years ago, most of you know this, I was profoundly blind, and I was a quadriplegic. It was an operation that went sideways. They saved my life, and so I'm eternally grateful. But I had to fix my brain myself. Now, that's a whole nother story, possibly a book, I don't know. But I did fix my brain, and I got nominated for a TED Talk, actually, to talk about how I did it. And so the thing is, this brain healing thing made me realize, as I was doing it, I had to get my eyes back. You know why? Because I wanted to never lose the ability to see things like this right here. This stuff was the most important thing for me to see in my entire life, besides my children. Okay, so looking at the sky like this, I couldn't lose. So in a sense, the desperation to fix my eyes led me to the fix. My visual center is literally all but gone. There's nothing left there, okay? But I see perfectly, almost. It's 98%. And the reason is because I figured out that the brain can actually be rewired. And so I rewired my brain through evolutionary processes that I can talk about in another stream if you like. But the bottom line is, I've been fascinated with astronomy ever since I was 9. Most of you know that I knew I was going to be an astronomer at age 9. Okay, and I never changed. So my mother would always say, "Why don't you get a job where you're going to be making some money? Why don't you be a doctor?" And I was like, because I love astronomy. I love the universe. I also love the deep ocean and what's going on down there. And as an astronomer, you have to learn about the deep ocean. Isn't that wild? But you do. And you have to, because you have to understand how the Earth works. So you can then apply that to planets around other stars and how life may develop there. And it's for the very reason that we look deep in our oceans that we're going to go to Europa looking for life. Europa's a moon of Jupiter. What? Yeah, it's a moon of Jupiter. But it has an icy mantle. Okay, and that icy mantle, besides me going out of focus, that icy mantle is something that covers what is known to be an ocean deep beneath the crust. All right, and that ocean down below is something that is really, really important, because in our deep ocean we saw hydrothermal vents. Around these hydrothermal vents, where no life should be. Okay, we found not only life, but many, many hundreds of different species hanging out at those vents. You always hear about the giant clams, the tube worms, and the bacteria, and the little crustaceans. But there's way more than that. Okay, and so those hydrothermal vents are a breeding ground for life. So we thought that, hey, if they're doing that down there, they can't be using the sun, which is photosynthesis, right? Converting light into energy, right? That's what, plankton does. Phytoplankton, also known as blue-green algae, okay? That's what that does. However, when we're talking about life in a deep ocean vent, there's no sun down there. So they have to use different processes. Note that process, one of them, okay, that's very important, is chemosynthesis. Chemical synthesis to create energy for life. And that's exactly what goes on down at the ocean floor. And chemosynthetic life opened a huge door. Now, yes, we knew that chemosynthesis had occurred and was occurring on the planet, but what we didn't know was that such a copious amount of life could exist on the ocean floor. All right, in these dark, forever dark, permanently dark regions. So we go to Europa and say, hey, we discovered there's an ocean under its surface, under its icy mantle. What does that mean? It means that perhaps that there might be life down there too. And that is another story. Okay, we'll do that on another talk. So, that said, when we talk about going to Europa, we said, hey, let's set up a mission to go to Europa. So NASA did, and they've got it. It's on the way. It's called the Europa Clipper. Exactly. And the Europa Clipper is going to be looking for suitable landing sites for the Europa lander, which is going to go and try to get down in one of the deep fissures on Europa. There's really deep fissures, and inside those cracks, if the tug from gravity of the outer moons, Ganymede and Callisto and Io and Jupiter, need and squeeze Europa just right, we see water coming out, and the water contains H2O, of course, and it contains other organic compounds. That means that the building blocks of life may be getting manufactured inside of Europa. So we're going to go, and if we can get to one of those places where the geysers periodically open up, and put a little, and one of the thoughts is a mini sub, like a cylindrical mini sub that can go down like a sounding rod and go whoop, go down into the hole, and find its way to getting into that ocean. It might be able to detect life. Wouldn't that be something? Now, we are trying to detect life hundreds of light years away, right? The James Webb Space Telescope has questionably, it has to be confirmed, it's going to be looked at more, but it may have found a compound called dimethyl sulfide in the atmosphere of one of the Kepler candidates, one of the Kepler planets, actually. It's confirmed. And this particular compound is something that every one of you know. And I've told you this, so some of you may know that already. And what that is dimethyl sulfide is the smell that you smell when you're going by the ocean at low tide and you look at your partner in the car going, hey, did you, no, I didn't, did you? No, it wasn't me. It smells like that. It's kind of that raunchy smell of the clam flats, the mud. And what you're smelling is dimethyl sulfide. And where does it come from? On Earth, it is only, solamente made by life. So if the James Webb findings can be confirmed, well, now that's a whole new ball game. Now, guess what? We have found life with the James Webb. Now, it's only going to be microbial life for sure, but this big planet that we're looking at is a little bit larger than the Earth, but it doesn't have an oxygen-nitrogen atmosphere like we have. It has a hydrogen atmosphere. Now, you might say, well, then how can we have life? Well, because you can have microbes that don't rely on oxygen the way we do. Okay? Witness the hydrothermal vents and the bacteria that we see down there. Okay? Some of them, again, chemosynthesis, not photosynthesis. They don't make compounds to work their metabolism, right? So that's going to be a very interesting finding. Now, the trouble was, when they saw this, they said, that's a lot of dimethyl sulfide. And the thought was, well, maybe this is a planet that's bigger than the Earth, and maybe it has more water on it than the Earth. And as that turned out, the finding was true. It is a bigger planet, and it does have more water than the Earth. The only problem is the dimethyl sulfide finding didn't show up in the next read by the James Webb. So how do you explain that? Right now they can't, but right now they're not really trying. They're going to do repeat observations to see if they can see dimethyl sulfide. And if they do, well, then it'll be somewhat of a foregone conclusion that that'll be a compound created by life. So wouldn't that be exciting, huh? I like it. Hey, So, all right, so I know that's kind of an aside, right? But that's me. I'm always doing asides, all right? Let's go see our Benson telescope. I'm looking over here at this right here. Now, it's right there for you, but it's there for me because I've got big monitor screens. It's like a carnival here. Lights everywhere, okay? And I can see that there's a lot of motion out there still, but hey, we may give it a try. Let's refresh and get the latest view here. There's those little clouds going away. That's a beautiful sky. Yeah, that's probably the moon right there. Okay, moon is around first quarter. That's probably the moon. So that's going pretty well. And speaking of moon, well, we have moon as well for you, but we'll get to that in just a bit. Okay, so let's go now to another object. I want to show you how we get from this, okay, to something like this. Now it's a different galaxy we're going to use, so you're not going to be bored by the same one, okay? All right, but this one is another one that's very interesting, okay? And at Cornucopia, this is your favorite galaxy, I think, from what you told me. And Cornucopia asks, only biology makes it. Yes, that's true. Only life, biological living creatures make dimethyl sulfide. You're absolutely right. You know, and so I want to now show you what we do. Now this is my Photoshop, and what I've done is I've written a bunch of different routines within Photoshop to help me do some of this. This is one of them. You know, I'm going to be setting some levels. Okay. Now if you recall when we look at in SkyTour Livestream, when we're stacking, we have a curve, right? We have a curve that goes up and down, okay? And I call it a histogram. Well, that's this, okay? And this is a red, green, and blue curve, okay? But you can't really see it as a curve because it's small, all right? But then this is the dark level. Remember I had that dark level we bring in, and I bring that in, and it gets darker in the background, and we're not losing any data. We're just getting it to the point where the dark level is going to pick up just the data, right? And then we do a balance of the color, which I'm going to do right now, like we do. And so now you'll notice it changes a little bit, okay? And so at that point, now we're there. Now the next one is another color balance, a balance rather, and I'm going to bring out some of the subtle details. Remember that dynamic range thing I talked about, where there's data hiding in the very, very bright areas and data hiding in the very, very dim areas? I want to bring them both out, okay? And so that's what I'm doing here. And then we're going to bring up another set of curves, okay? And this one looks really interesting. This is called curves, right? And what I'll do is I'm going to click this hand, and I'm going to then click on this and drag upward, and it makes it brighter. And I'm going to click out here and drag downward, and we get contrast. See that? So this is a way to actually, with literally just the mouse, pull out data. Look at that data. We haven't seen this before. Now we can. All right, and I'm just going to adjust this a little bit so we don't lose all that much of the areas I want to see. I'm going to bring down these. This is the absolute white area. If I bring it way down, you'll notice that we lose some parts of the galaxy's core. I'm going to actually put it right about here, just below the top, and I'll raise this a little, because the idea is we're making kind of an S curve here. This little S, see, it's a bad S. I'd get an F in penmanship for this S. I know I would, and you don't have to mention it. Shh, don't tell anybody. Okay, but what this does is now it gives us the opportunity to now see a processed image. Okay, so if we zoom in now, I'm going to show you this. Okay, here is the noise that we get with our camera. But then you got this greenish pixel and this red pixel. These are called hot pixels. Okay, yeah, they're really cool looking, very nice looking. So we call them hot for that reason. But we call them hot because they're just in the way. They don't belong here. So we got one here, we got one there in the galaxy. You see they're kind of sprinkled all throughout. But I wrote a little piece in Photoshop that will get rid of those. So, well, this will remove all hot pixels. So now watch right here. Watch these two right there. Ready, set, go. And they're gone. Okay, all of them are gone. And it doesn't affect any of the rest of the data. In fact, it improves the data. So now we're looking at the Sombrero Galaxy. And I remember in one of the past chats that Cornucopia actually said, hey, that's my favorite galaxy. Well, here you go. This is the processing going on. You'll notice we zoom in, you'll see another thing, okay? As we zoom in, you'll notice that there seems to be colors in here. That isn't really there. And so now the next step is to remove that color noise, it's called. All right. Now, I'm not expecting you to remember this. I'm just trying to show you the really cool stuff that we do to get rid of things, okay? So I'm going to go like this. You'll see this. There's that color noise. Now what I'm going to do is I'm going to remove the color noise like now. See? There's the color, and now it's gone. And this is very much more realistic. So when we come out, okay, color noise is gone, but it's still grainy, isn't it? We're going to fix that too. All right, so now we have that. Now I'm going to go back in and do one more thing. I'm going to go back into that curves thing that we did before. And what I'm going to do is increase the faint areas. And to do that, I'm going to start by doing it like this. I'm going to come over here and go like this. Okay? And then come back down to the dark areas and pull it down. And this is typically this is a balance. You're going to do a balance of stuff here. So if I move this, you can move these spots in the curves too. And then take this guy and move this now. We're going to try and get a little bit more contrast in here with our background. Okay, like right about there. That's pretty cool. Again, another S-curve. Again, you don't have to remember any of this, but this is the processing I do behind the scenes, for you, so you can actually see what goes on when we do this. All right, now when you look also at this object, you say, well, it's still kind of noisy, Mark. I mean, what do we do with that? There's a couple things we can do. We can go in and say, hey, we can get rid of the noise. Okay. So if we come in here and you see the noise there, well, there's look at a noise reduction. Hey, slide that over. Oh, hey, that looks pretty good, right? And then if we come out and look at it, say, well, now it just looks blurry. Yeah, that's no good. So we go into Photoshop right up there in the corner, and it says history up here. And we click on history, and we can now take back that last thing we did. See? So we can literally go back through all the steps we did. We can go all the way back to when we first opened it. Look at that. So we can just find our way through the whole thing, everything we did, until we get to our location that we entered in just a moment ago. But now, there are, as you can imagine, tools specifically made for things like this. And one of them is made by a really great guy. He makes these filters called RC Astro filters, and one of them is Noise Exterminator. And I have settings that I discovered work the best, and that's there. Let me see if I can bring it down here. It doesn't look like it wants to. There it goes. So you can see them here. Make sure you're at 1080p so you can read any of this. And when you go back later and look, you can kind of recreate and copy the things I'm doing. Okay. All right. So let's start this off, and let's bring this in. And you can't see it, it's just out of view, but it's going to do it now. Watch the noise here, and watch how it doesn't make it just blurry anymore. It makes it look really cool. Then I got another little surprise waiting in the wings for this. Okay. So, okay, now that doesn't look like it's just blurry. But I have another thing now we can do that I wrote, and it's this guy. Okay. Not that guy, this guy. Okay, this is called a structure definer. And what we're going to do is we set up some filters in Photoshop, and then by using a brush in Photoshop, which is like a paintbrush, it's going to paint and pull out detail in here. And you'll notice that as we come in here, you'll see that this is an image showing the galaxy with some detail in the background. That's going to be the detail we work on. Okay, so it's going to come in here, and we're going to do it, and I'm going to pull it out. We're going to go in here. Now watch, as I cross this, look at that. Now you see the detail in this central disc, don't you? And then here, and then here. You can even see the start of the spiral arms in here now. Okay, this is all part of doing this processing. Now, I'm going to tell you right up front, I'm doing this very quickly. Typically, I'll take a lot more time doing this with the images that I present to folks. But this is an example of the images that we create, that we put in our paywall for people that are in the Patreon. So these are all available through that. Now, I'm going to do one more thing while I'm here. I'm going to come in to do something else I want to do, and I'll do that from our galaxy shot. I'm going to see if the color rendering in here can show us a little bit about what's going on. That's a little better. And let's see if we can move this. So you can move the colors and change the colors all around. Okay, but the actual colors, right, are more like this right now. This is more of the color. And what I can do actually is I'm going to try and do another color correction out here. And so it kind of fixes space but leaves the galaxy alone. Look at that. There you go. That is the Sombrero Galaxy with our Benson high focal length system. So it's a close magnification. It's really good. I know that people are writing messages in here. I do want to get to them, and I promise I will. All right. I just saw Tiffany, your message. Woohoo! Can't wait for Contact in the Desert. That's CITD. That's what she wrote. Okay. So there. So now what I can do here is I can say save as, and we have a set of images. These are all the images we've taken with SkyTour over the last year or so. There's quite a few of them, and we're going to set up a new directory, and it's going to be called the Sombrero Galaxy. And I always give a date on it, so it's going to be 04 dash, and this was on the 17th dash 26. All right, and we say that, go in, and we'll save this processed Photoshop document, a PSD. Okay, and then we're going to come over here and then do this. We're going to then export it. It kind of is similar to what I do in the stream, right? I'm going to export it as a PNG. So we save exactly a scene, and then we export. So now we come back here, and we come up, and let's do modified, and let's see, Sombrero Galaxy, and go in there. And now we'll come down here and just say the same thing. I'm going to just add to the label Sombrero Galaxy, and then 04-17-26. Okay, and save that. And this would be an example of an image that would be available to you if you were going to access them with Observer and above. So if we close in, you can see now the subtleties. Remember the Hubble image of this? I don't know if you saw this, guys. The Hubble Space Telescope took a gorgeous image of this, and you could see some real complexity in this. And guess what? We can see it too. It's just not as clear as a spaceborne telescope, but we can see it there. Look at that. Now, this dark dust, in case I missed the question in the chat, this is dust that rings a lot of galaxies. The next one we look at is going to show some of this as well. Okay, and this dark dust is something that is, again, as I mentioned, produced by supernovae and red giant stars that are puffing off their outer layers, making these things we call planetary nebulae, like the Dumbbell Nebula, the Ring Nebula, and so forth. And that dark dust is where, again, life begins. All right, and so it's very appropriate. In fact, you know what? Dark dust is my hot button. What can I tell you? You probably figured that out by now, huh? Yeah. So, in any case, I hope that this is something that you like seeing how we create this. Now, what I'm going to do now is I'm going to bring up another one. Okay, we can actually close out of this guy. And there's the Hamburger Galaxy. We're going to close out. Before I do that, I'm going to try something else here. Let me see if I can. Yeah, I can just a little. I can darken up the background just a little. Look at that. Wow. Yeah, not bad. Okay, so now what I'll do is I'll resave it. Yeah, that's what I do. I do a lot of revisiting to the images to get them looking right. This is subtle data that was so hard to acquire in the past, but now it's actually pretty easy, thanks to this particular telescope. Okay, all right, so I got that there, and I'll just export it as a PNG file one more time, because that's the process. Remember, you always stick to your processes. All right, and we'll come out of Sombrero, go into Hamburger. Anyone listening to this is going to say, what is he talking about? Get out of his Sombrero and get into a Hamburger? What in the heck? Yep, going to replace it. All right. Okay, and then we can get out. Now, I'm going to go to, these are some of the ones we did before. I'm going to go now to one of the other ones that I think is pretty cool. And we're going to do it from our from here, and we're going to go into, let's see. Oh, that's Clem. Clem is my character I created. Let's go to these guys, sharp captures, and we're going to go to 417. And we have, there should be Needle Galaxy in here. We have Black Eye, which is really cool. And Needle Galaxy. Let's do Needle Galaxy. All right, we'll do this first, and that's the one I was going to. Okay, now process this in there. That's all the PNG files that we made. This galaxy looks like this. Okay, you can see that little tiny. It's right on edge, almost perfectly on edge, and it looks really cool. Okay, and now let's go and grab the fits file again. This is something. Now I've got only 21 frames of this guy, but watch. When it comes in, you're going to say, that's very unimpressive, Mark. That's very unimpressive. Look at that. What a beautiful galaxy. Highly unimpressive. However, never fear. The galaxy's here. Okay? And so what we're going to do is we're going to actually start to pull the data out of the background. Right? And just by moving these little guys, then I will, of course, color correct that kind of magenta cast in the view. And now we're going to do it here. Oh, look at that. Now we're getting some stuff. And we'll pull this down. And look at this. This is one of the most spectacular galaxies in the sky because of its, number one, its size, but because of what we're seeing. Okay, it's right on edge almost. Let's go and grab this and move that up. And then darken the background. Look at that. Look at that. This is amazing. See how quick this happens? And now we fix our curve to be more of an S curve. We'll take this is the white area. We take the whites down so the nucleus doesn't get blown out. But you're going to see some neat detail in here, and I might be able to take this up a little higher. Yeah, look at that. That's a little too much because it starts to induce more noise. But we can actually go like this. And we'll try that. Like last time, you'll notice that we have some hot pixels. And if you keep your eye on those hot pixels, you won't see them for long because I'm going to be taking them away. Ready? Watch this guy, that guy, and this guy. Ready? 1, 2, 3. Boom. So they're all gone. All right. And now we have this galaxy left. Now this galaxy is not perfectly edge on. It's sort of just slightly tilted. So we're kind of looking along the disk of this galaxy from just above it. So you'll actually see spiral arms going in a circular pattern around this. Okay, so let's start to pull those out, shall we? And the way that we're going to do that is we're going to come in and grab our curves. We're going to bring the light up on that a little more. Okay, and we're going to pull this up to here. Notice the dark convolutions in this dark dust that's in this galaxy that runs right along the center of the galaxy. All right, and now I will just start to darken everything up a little bit, and that's it. Okay, so this particular galaxy then is neat. Now what we're going to do is come in here and, like before, we're going to get rid of the noise from the color. All right. And you may not be retaining some of this, but what's important to understand is how we do what we do. And I'm showing you what we're doing behind the scenes so you can get an idea of what it is we actually go through. All right. Now, this galaxy then has all this beautiful stuff in it. And so now at this point, I'm actually ready to get rid of our noise on this galaxy, which is cool. All right. So I'm going to go down to this noise exterminator that I mentioned to you, and we're going to do it again. So we'll see the progress bar appear here. Now watch this noise go away. It's pretty cool. Yeah, so here it goes. Yeah, there we go. Yep. Neat stuff. So now what we're going to do is come in here and now do our other guy that I produced, which was this. That's the wrong one again. This guy. It's a structure definer, and you'll notice this one is going to show us. It's got some really bright stars in here that kind of make these colors, but then the center core here is actually pretty bright. So with details, so we're going to go in there and grab this detail. All right, and so here's how we do it. So we're going to start right out here and start moving down. And you'll see that we're actually enhancing all of this interior structure in the galaxy. Look at that. All right, so now if you turn your head to the left, you can kind of see how we're kind of looking down on top of a big circular galaxy which has circular spiral arms. You see that? And from the edge, it kind of looks like this needle. So this is why this is called the Needle Galaxy. Pretty neat. That's really neat. Now I'm going to do one more thing before I save it. I'm going to come in and just do one of these things. You'll notice that we have all this stuff out here, okay, and we don't need that there. Oh, sorry, I was in the wrong one. I'm going to get over here. I was in the wrong. This is the one I want. You'll notice that we have just a little playroom here before we get to the peak, and then we can actually put that darkness in there, okay, adding the deep space black, and then pull in some of the detail. Look at that. That is just gorgeous. That is just gorgeous. Well, let's try one thing. Let's try. There we go. I just did another color correction, and you see the brown dust is now brown. Okay, just beautiful. So this is the Needle Galaxy, and like before, I'm just gonna save it, and I'll save it out to our repository that I have, and I can go here and come out to here, and then we're going to say Needle Galaxy, and I'm going to give a date again, 04 17 20 say 26. All right, and then go in there and then save it as a Photoshop file. Okay, so there it goes, it's saving, and we can already go and save it now as a PNG. Yeah. And there you are. And now I'm going to just go out here, go out to the Needle Galaxy location and save it as a PNG. And we're going to just say the same thing before, Needle Galaxy 04 17 26. And that's perfect. And then we can save it. Now that image is saved. All right. So there you see how we're doing this, and that's pretty cool. Now, there's a few things that are neat about this, and I won't do any more of these per se, and I'm not sure I want to do any more of the processing stuff with you tonight. What I may want to do though is show you something else which I think is really interesting, and that is something like, so right now the moon's out. It's a first quarter moon, right? And if we come in and we go look at this, let's hit a refresh, okay, and see, okay, well, there's our moon up there, and you notice it has some clouds on the horizon here, but those are on the west, so those will be either heading southeast or they will be heading toward us. These clouds are in the south here. Okay, so the whole southwest is taken up by clouds. That dome right there is this dome right here. Okay, this is not our all sky cam. We're bringing our Sonoran all sky cam here, and it will be set up. A lot more data, a lot more sensitivity. It'll just be stunning. Okay, so we'll get back to this. Again, I'm waiting to see what we get for a wind speed out there. Okay, so the next thing that we want to do here tonight is I want to show you something. Because the moon is first quarter right now, I thought it might behoove us to look at the moon. But I'd like us to do it in a really cool way. And the way I'm talking about is with this free moon browser that you can get on your computer on the browser, okay, Firefox or Chrome, and it's actually called the LRO Quick Map, the Lunar Reconnaissance Orbiter Quick Map. I teach classes on this thing, and the reason I do is because there's so much to it. For instance, I'm in the 3D mode. We don't have to be. We could just be on the front side and the back side. I like the 3D because it allows us to zoom in a way that's really cool. We can spin things around. Okay, this is a place called Mons Pico. Well, you don't know that, right? Because we don't have a name for it. And look what you can do. You can literally move around. You can actually rotate from your cursor. All right. And when you zoom in on this, watch this. It looks like there's no data, right? Oh, contraire. Look at that. We can see all kinds of data. Look at that. Look how close we are. We are now on a hill on the moon called Mons Pico. And we can actually rise up and look out and say, hey, that is the crater Plato. That's the wall of Plato, which is, let's just zoom out. Okay, that's Plato, the crater. It's 60 miles across. All right. And what I want to show you with this is how this works. Aurelio Maraca asks, can you 3D print craters? Yes, I can. Okay, I sure can. And I do. I was talking to Trent Hare, who was with the U.S. Geological Survey out in Flagstaff, and he gave me access to all the lunar data, very, very high res, and I can grab that data and make prints. You can do that in here too. You can actually say, I want to 3D print something. And so you could actually say, all right, I want to 3D print this area. So what you do is, well, I should wait until we get to it, just so I don't go ahead of myself. But so when we look at this guy, we say, well, how do you know what its name is? Well, we go into Add Layers, okay, and we say Browse Layers. Okay, there's a lot to this. You can see all the geological data and etc. Then we go into Overlays, and one of the overlays we want to do is nomenclature. Okay, in other words, the names. So you want to see names of things. Well, there you go. Remember I told you about Mons Pico? Here it is. See, right there. All right. And then we have other objects out here. We have Pico E, Pico D. And then as we zoom in, sometimes they will actually label some of the smaller craters. Like this is Pico K. All right. And this is overlays for more passes from the Lunar Reconnaissance Orbiter that's circling the moon as we speak. And you can actually see all this data. Now, you might say, well, what good is it if we can just look at it when can't we actually do other things with it? And yes, we can. Now I'm going to show you this too. Okay, see this right here? You'll say, wow, look at that. A bunch of other meteors struck here. What's going on? And the answer is not necessarily. Because what we're looking at possibly here is that this is kind of a line, isn't it? All right? And then this ends in like a larger clump. Now this line could actually be the key to our lunar survival. What? Yeah. This could be an area where we have an underground subterranean lava tube on the moon. And when we see these little pits along the way here, this means an area where the ceilings have collapsed. Okay, so there's hollows under here. And if we go to maybe here, maybe underneath here, we don't know, there might be an uncollapsed part of the tube which we can set up a base in. And why would we do that? We would do that because there in that uncollapsed tube, the lunar soil above our heads would protect us from ultraviolet radiation from the sun, cosmic rays, and we would actually have protection from radiation that could harm us. And that's essential if we're going to go to the moon, isn't it? Right? So I think that's pretty cool. So now these are things that we can see on the moon when we look with the telescope, but what we can't see when we get close to the moon, right? We can't see things like this, boulders on the edge of the craters. Look at that. Those are boulders, all right? And we can actually measure roughly the size. And here is one that's sitting right on the edge. The sun is low, and you can see that they make shadows. And those shadows look really interesting. Now we're getting a little close, so we're getting beyond the resolution. Okay, we're literally looking at an area that is literally just a few tens of feet across, few tens of feet. And the smallest object we can see in here, these are rocks that are maybe about 5 to 6 feet across each. Okay, so you get an idea of how difficult it is to see, for instance, the Apollo landing sites. And so that's kind of cool. But speaking of those Apollo landing sites, why don't we select those? Let me go in and grab layers. Let's go find the Apollo landing sites. They are in, I think, is it in featured images? Let's find out. Uh-oh, waiting. Yeah, how about that? Well, you know, never let a computer bog you down. We can actually start this over again if we have to. Sometimes this guy will actually hang on you, and that's not our fault, not my fault. Everything in my hands working fine. So sometimes it does that. Yeah, so we'll stop this right now. Tell it to stop. All right, and now we'll start over. So we do. All right, so we start over, and let's get this to give me a new view of this. Let's see about this. Okay, well, obviously, we're going to have to quit this and do it again. Hey, look, it's our galaxy. All right, so let's bring this up again. I don't know why it does that to me, but it does it sometimes. So let's open a new window right here. There we are. And actually, this is helpful too. You notice this is our view of our observatories. There's the Sonoran view, and this is the Benson view. We do have some clouds. You see them? So it probably wouldn't be a good idea if I click on this. All right, and we'll get back to the moon in a minute. You can see that we have 26-mile-an-hour winds out there that are coming into the evening, and then well into the evening after just about midnight, okay, it's going to actually drop to about 13 miles an hour, then 11. So it's going to keep going, you know. And Marianne Robb is here. How you doing? Nice to see you, Marianne. Yeah. And let's now go to our LRO quick map again. All right. So it's LRO LROC quick map. Look that up. You can get in and you can do all these things too and be able to see everything on the moon. Now this, when it comes up as the front face of the moon like we see. Okay. Now the moon does a little bit of this motion, okay? And that little bit of motion is something that, okay, will allow you to see a little bit more on either side, okay, as the moon orbits, because it doesn't quite orbit perfectly around the Earth. All right. So what we're gonna do is add our layer back. Let's try this again. Here's the Apollo sites that I wanted to show you. Okay. We're gonna do. We're gonna turn on Apollo 12, Apollo 14, Apollo 15. Okay. And then come out of there. There are those dots. Now, let's take a look down here at Apollo 15. Now, there are traversal tracks that you can see. All right, and if you look really carefully, all right, we move down here. You can see the tracks right here. There's tracks right there that the astronauts left. Okay, there's the rover. Now I know it's got this tracks in the way. And what I'd like to do is get rid of those, and I will figure out how to do that at some point. I know that right now I don't like those. I want those to be gone. And there is a way to do that, and I just don't know what it is yet. And I gotta figure out how to get rid of that. But you can still see. You can see this is a traversal line right here, created by the lunar rover. Okay, and in you see other lines that are, again, I got to get rid of these. There is a a dimmer switch basically, but it doesn't. Oh, there it goes. There we go. Excellent. So let's move those down. Okay. Now as we zoom in, you can see all the lines and traversal lines, and this is the descent stage of the lunar module. That's its shadow right there. Okay. And we can see the rover with its shadow over here. Actually, I think they called the this other thing the rover out here, but I don't think these are lined up exactly, because I do know that this is the lunar module with its shadow, so they didn't quite get it right, but that's okay. But there you go. So that's pretty far that they've moved. Look at this one. This traversal was huge. Okay, can you imagine going out there and going way out there? Now that must have been a long distance, right? Yeah, it's really not that big. So if we actually want to measure that, we can figure out how far they went just by grabbing this guy here, which is you go into this, it's called a spanner, and then you grab this little path tool, and you say, okay, from here to here, how far did they go? They went 5 kilometers basically from the lunar module. But guess what? They never lost sight of it. Okay, they never lost sight of it because there's no air, so the thing wasn't fuzzed into the distance by atmosphere, so it was very, very clear to them. So that's kind of cool, and we can delete these as soon as we bring them up. Okay, all right, so that's Apollo 15. This is Hadley Rill. When you say, well, it's a rill, but what is a rill? Well, if we actually go into the 3D globe view, okay, and go into the Apollo 15, which we're slowly getting to, okay, then we can actually zoom in and do this, and now you see what the rill is. Okay, it's actually, again, it's a lava tube that's collapsed fully. Okay, look at the boulders on the side, huh? Isn't that cool? We can also, in the 3D globe, go inside, get right down and say, wow, let's look out there. Look up. Look at how this would look from this point of view. That's kind of neat, and I think that's neat. Very, very cool. So that is the 3D globe view of this, and this gives a real perspective on how far things are on the moon. Now, if you want to look at the profiles, like how high up from the bottom of this are they? Well, we go back to our spanner tool, and by the way, if you have questions about any of this, you can always ask me and I'll tell you. So you go from our spanner tool, let's do this, and let's say, okay, from this particular point called Station 10, let's go from here all the way down into the valley. See, it follows the contours. How far are they from the bottom of the valley? It's literally almost a kilometer, 0.86. But then you say, well, can we get the actual shape of that path? And you go into inspect, and you get 2 images. All right, and we don't use this one or this one typically, but we want to just use the regular terrain height. And notice there's a yellow ball inside this blue line, and it starts where I put this here. So at the top now, we are here, and then as we get to the bottom, all right, it's there. Now, what does there mean? Okay, first of all, we have this altitude here where we're sitting. This elevation, if you look right here, okay, terrain height in meters, watch this. Okay, terrain height is now 1900, right there, 1906 minus 1906 meters. Now, wait a minute. What do you mean minus? Inside is deeper. What's going on? It's minus 1906 meters below the mean radius of the moon, which is 1700 and 30 kilometers. Okay, so what that means is there's a standardized radius of the moon from the center, and then we figure out what's above and below it. And so this right here, this location, is literally it's right here, and it's actually it's minus 1907 meters. So it's actually down below the mean radius of the moon. And then this here is even further away, so that's down the bottom, and that's minus 2,226 meters. So it's literally over 1,000 meter drop. Okay, it's literally, you know, well over 1,000 meters. It actually starts here. Okay, so minus 1913, and then goes all the way to the bottom, which is minus 22. Okay, so actually that's less than that. Sorry, but it's several hundred meters down. And that's actually kind of interesting because it shows that this area here, if you kind of started walking down this cliff here, it'll be pretty difficult to get back up. This is actually not exaggerated terrain. This is the way it is. This is how it actually looks. Okay, so this is neat. And by the way, I know by showing you this, I'm ruining some marriages and relationships, because if you're interested in this stuff, you're going to start going through it, and you're just not going to stop. You'll be late for dinner. You'll be late for meetings. Maybe it'll even get you fired. But I will say this. This Hadley Rill area is neat, because see how this is sort of a pit, this is sort of a pit, this is sort of a pit. These are the collapsed ceilings. Okay? Now what's in between will be like rubble piles maybe underneath, but there'll be voids under here, possibly. We can follow Hadley Rill around, okay, and see where it goes. And again, where it gets flatter and not as deep, that's an area that hasn't collapsed yet. Okay, and these rills are very, very common on the moon. All right, look at that. All right, and so these are massive, massive, massive constructions. Oops, sorry about that. Let's go back and look, in fact, at how far they traveled in the Apollo 15. Okay, 5 kilometers. This is way longer, way bigger, many kilometers. We do a 3D print of the Apollo 15 landing site, and it comprises this whole area right here. And it's just beautiful, and people buy them all the time. They're just neat. All right, so this is Apollo 15's landing site. And yes, we went to the moon. And so this is kind of interesting. All right, I know that people don't like to necessarily believe that, but that's just because they don't have access, or don't know that they can have access to this data. Okay, so now Apollo 14, all right, we can actually go to that. We'll zoom out and zoom in to Apollo 14. All right, here's Apollo 14. Again, its traversals are shown here. And with the 3D globe, it doesn't actually, it doesn't allow me to dim them. So let me do a orthographic near side. Okay, it'll go away for a minute. Okay, and then we got that. So now I should be able to dim these out. See, look, it proved me wrong. Oh, that's Apollo 15. Sorry about that. Let's delete that one. Now Apollo 14 will dim out. Okay, see? So now we zoom in on this one. Okay, and you can see tracks already. You can start to see the trails. All right, interesting, huh? How this actually turned out. All right, this is an area. Let's see now where it tells us the objects are. Okay, yeah, they walked all the way to these different locations on 14. I think some of you may know. I forget when. I think the rover started on 15, didn't it? It's possible. So so this, again, the light on the moon right now. Look at the cratered areas. It had to be an incredible and difficult process to figure out where they were going to land on the moon, right? And that's really a problem. Now I'm going to show you this one here. Notice over here, it's in the dark, but this is the LRRR. That's the lunar ranging retroreflector array. Okay, and that was made by the university where I got my degree. And so there's one in the lobby of the science building out there, and you can look at it and see it, and you can see exactly what it is. It's an array of something like 24 by 24 round objects that look like bicycle reflectors, but they're not. They're very elaborate reflectors called corner reflectors, which are what bicycle reflectors are and car reflectors are. But they're actually obviously very advanced because they had to last for like hundreds of years on the moon. And these little prisms are called corner reflectors because what they do is they reflect a small component of light back in the same direction that it came from, which is exactly what you need if you're going to send a laser beam to the moon and the moon's sort of on an angle from it. It could hit like at an angle like this, and you get a reflection directly back. Instead of getting a reflection that comes off and goes up and you never see it back again, the corner reflectors reflect a good deal of the light back to your eye. So by the time the laser from the Earth reaches the moon, it's literally well over 2 to 2.5 miles in diameter, the beam. And that's with a high-end, very, very powerful green argon laser being sent from, say, Mauna Kea, above most of the air on the Earth. Okay, almost. Okay, it's above 14,000 feet. So when you send this pulse, it expands and distends to that size because it's something called dispersion. As perfect as we are sending out this parallel beam, it's slightly not parallel. And so it grows to over 2.5 miles in size by the time it gets to the moon. Okay, that's pretty cool. And then a little bit of that, a far less little bit of that comes back. And if you have a very sensitive detector, you can detect it. And that's what we do. And that's how we know how far the moon is from us. Why? Because we know how fast light moves. And so based on the time it takes, about 1.3 seconds, we can calculate the distance of the moon to the millimeter. All right? And that's pretty cool. And the moon is spiraling away from the Earth every year by about this much. Okay? By about 3 centimeters or so in distance. And the reason that's happening is the same reason that our day is slowing down. Wait, what? When we were first made on the Earth, that is when the Earth was first made, our day was about 4 hours long. The object that hit the Earth that tilted us to give us the axial tilt and produce the moon in the understanding we have, that circled the Earth for very close to us for a long time, and so our day started out about 4 hours, and then it eventually got to 6 hours, 8 hours, 12 hours. Why? Why did it slow down? Well, because once it made an object that was circling around us, okay, that object is tugging on the Earth. As the Earth is rotating, we had something else going on the Earth. We started to get tidal bulges, at first of molten rock, okay, and then oceans. And as it's going around like this, as the moon is out here, you can see it tugging on this part of the Earth just a little bit, slowing it down slightly, okay, as it went around. And by doing that, by slowing it down a little bit, it actually causes the moon to speed up a little bit. So Earth slows down a little bit, the moon speeds up a little bit. So over time, the moon is spiraling away from the Earth over time. And that distance is about 3 centimeters per year. Okay? Now, that's a momentum. It's called momentum stealing. The moon is stealing our angular rotation, which is called angular momentum. And so, because of that, our day went from 4 hours to 23 hours, 56 minutes, 4 seconds. Kind of where we are now. But it's still getting slower, right? Not by much, okay? But eventually, what could happen is the moon could end up being tidally locked to the Earth, so that one side of the Earth will always see the moon in the sky, okay? Just like we see one face of the moon now, but it's still going around the Earth. If it spirals far enough away, the Earth will slow down enough so that the rotation speed of the Earth will match the orbital speed of the moon around the Earth, and therefore they'll be locked to each other for eternity. Now, that sounds romantic, a full moon. You'll see the moon go through phases, but it'll be at one point in the sky, which is kind of weird. All right. Now, the thing that's interesting is that when you watch the moon in that part of the sky, let's say you're at new moon and it goes into nighttime. Well, the moon is going to block a portion of the sky, and people in that part of the earth will never ever see it. And in fact, people that are on the other side of the earth, when the earth rotates into that position, they will see what you couldn't see behind the moon because the moon is blocking it. Kind of cool, you know. So there's a lot of things. I do I do want to also let you know that this is not all there is on this Lunar Reconnaissance Orbiter. Okay, a quick map. We have tons more layers. Okay, we have Apollo sites, we have past mission sites, future mission sites, future moon landing sites that have been plotted out already. And this is, by the way, dynamically updated. This is online. So you're getting the latest and greatest data. And that's the cool part about this. And if you go into the 3D globe, it's kind of cool. And I'll do it again here. We go into the 3D globe here. And it goes away for a minute, and then it comes back, just like we saw it. Okay. One of the things that I like to do in the 3D globe is, like, here's Copernicus crater. Okay. It's a terraced crater. See the terraces, down in there. Those terraces are basically created by the initial explosion of impact, and it goes out, it splashes, and the central peak is like the bloop. When you see it in water, it goes, and you see that bloop when it comes up. Well, when they do it in rock, it freezes almost immediately, and you get a central peak. This is the bloop. Okay, in a crater like this. This is called a complex crater. There are simple craters, which are just bowls. Okay, here is a simple crater. Okay, this is just a bowl. See it right there? Just a bowl. It's just like a bloop. It just goes down and up. Nothing to it. And here's another one, a simple crater. But complex craters are, of course, more complex. And so we see a lot of crazy features on these types of craters. Okay. Now, one of the things that's interesting, okay, and again, we can, there's also this button up here allows you to circle whatever object you're looking at. You can zoom in, you can zoom out, you can accelerate around it if you want. Okay. You can see it from down low, see it from above. It's kind of cool to do this. And circle around, because if you're out here, you wouldn't even know there was a crater there because you're below the rim. So this is kind of cool. And then you hit escape to get out of that. Now, if we go in here, let's go onto the central peak of Copernicus crater right here. Okay, first of all, look at the boulders. Look at these boulders right here. Okay, isn't that neat? This is unprecedented detail from a lunar mission, and it's the Lunar Reconnaissance Orbiter, LRO. So it's really neat. Now, if we come in here, come right down here, we get as close as we can. Okay, and let me just back out this a little more and then come down. This is what it looks like if we're inside, looking at the rest of the crater. You don't even know it's a crater. You don't even know it's a crater. I can almost hear you saying, how big is that crater? Oh, well, that's easy. What we're going to do is we'll back out and come out to here. And we can get a good idea how big it is by going to our spanner tool here, grabbing this guy, and say, let's just move this over here and get an idea how big this is. It's roughly 89 kilometers across. Now, we also have a distance here that is complicated by the slope. Okay, but this is pretty close. All right, so there you go. And now we come here, you can actually move across the bottom. And by the way, this crater is actually minus 3,549 meters. All right, so a bigger object hit the moon here and is deeper. So the bottom of this crater is not the same as the bottom of other craters, which is not the same as the bottom of other craters either in terms of elevation. Now, why are they flat? Why are the bottoms flat? Okay, that's a pretty good question, because if you notice, you see how this is going down here. You expect it to keep going down and then come back up, right? It would if it wasn't being filled by something. So when this crater was first made, this is the inner part of the crater that's all flat outside the terraces. All right, it was scoured out, and then it blooped, and the bloop is this landmass that came sloughing back into the middle, made a peak, and then the liquefaction, that is the soil liquefaction that occurs when you have shaking and vibration, like we see in earthquakes, okay, stops, and now it's frozen for time, and all time, and so now you have the bloop here. But what's happening in the same time is the impact has gone deep into the moon, and the magma from inside the moon flows up to the surface and flows out as lava. Magma in the inside the earth is called is magma, and the melted rock is magma. In the earth, the melted rock is lava on the surface. I don't know why they want to confuse you like that, but it is. Okay, and then once the lava cools, it finds its own level, and so it makes sort of a flat bottom. But you'll notice there's all kinds of details in here and stuff. What is all that? That is later impacts that occurred. Now, the moon has been bombarded for billions upon billions of years. Okay? It went through a couple of bombardment areas where stuff just peppered the moon. There's literally this fine coating of dust on the surface of the moon you can find look at this, in the most magnified of images. The fine dust, they say right here, this fine dust is pulverized ejected material from previous craters. And look at that. As soon as we zoom in so far that we're almost at the limits of the resolution of the Lunar Reconnaissance Orbiter, and we can still see there's more craters yet to go. There's even more craters down here. So the moon has been peppered by tens of billions of impacts in all likelihood. Okay? And so that process is something that's never stopped. Those of you that were with us in 2019, on January 20th of 2019, noticed just after 11:30 during the height of a lunar eclipse that we're watching and we're streaming, a white flash in the lower left corner of the red moon of the lunar eclipse. We were one of 5 groups, as I mentioned, on the whole planet that actually watched the meteor strike the moon live. We caught it. Ta-da! That's so cool. So catching the dynamic universe in action is always a benefit, always cool. And that's what happens with Sky Tour live stream. That's really something we always like to do. So now let's go quickly look over here, and let's do a refresh here. Yeah, now that's the moon, as I mentioned. Yeah, we have some clouds. And we still have some winds out there, actually. So I do not think we should open the telescope tonight. And that's unfortunate, but we are at the mercy of the winds. But hopefully I'm giving you other things to enjoy, and if not, well, you could always complain to the management, but I think that's also me. Or Marianne. You can complain to Marianne. Now, here's something else. These I did not remove, okay? But this is another traversal. Let me go back into our orthographic near side here and grab it, okay? Now, this is neat. This is another Apollo landing. And what's interesting about this particular one, this was, you can see not only the flag and all these other things. Let me go back to the layers. Let's see if we can bring this down. Oh, on the wrong one. I think it's Apollo 12. Okay, let's come in here. Yeah, that's Apollo 12. Okay, so over here, when it's actually pointing out the flag, I mean, Mark, do we have any hope of seeing the flag? No, you won't see the flag, but you know what you might see? It's shadow. But look at the lines of traversal here. You can see where they were walking, and watch this. If we pull this down, now it becomes obvious. Look at all this. You see the paths on the moon. There they are. This is the lunar module right here actually, and here's its shadow. Okay, now these traversal lines are just a little bit off, not by much, but you see the flag. Okay, this is the lunar module right there, and there's the shadow of the lunar module. And then over here in this crater is something fascinating. This is Surveyor 3. What is that? Surveyor 3 is a lunar probe that we did a soft landing on the moon. Okay, the Surveyor 3 was the most impressive mission because it landed in a crater on an angle. All right, and the astronauts actually walked around this crater, and they went down and grabbed onto Surveyor 3. That was cool. So something that was sent up years earlier, landing on the moon, they went to inspect it. I thought that was pretty cool. And then, of course, they continued on their way. Okay, so they went to Surveyor 3, which is right here, and there's the Surveyor, and there's its shadow. And they did sample returns and stuff like that. And all these photos are available online, by the way. And that's the thing, you can actually go look at all the pictures from the Apollo archives. All right, if you look up Apollo archives online, you will find all the Apollo missions, all the film magazines, the Hasselblad images, all those are up there. It is so cool. It is so cool. I'm definitely intrigued by all of these things here. And I guess when we pull that out again, okay, you can see, let me make sure that was what I thought it was right there. Isn't it there? Yeah. Yep. So Surveyor 3 is right here. And let's come out of this right there. Okay, so there is the Surveyor 3. It had two big solar panels hanging at the top. You can look them up online. They're kind of an angle like this. Then a stalk, and then landing pads. And it was lit up in the sun. And here you'll see it's on sort of the dark side. The light is angling into the crater at just the right amount. So this side isn't illuminated yet, but this side is. But the Surveyor is sticking up just enough to be captured by the light, and then its shadow right there. Okay, so and then the back sides of these craters are illuminated, but the inside here, the near side, isn't, because it's still at that low angle slope. So that was pretty cool. That's pretty cool. So you can see now the other thing too is people look at these craters and say they look like domes. Well, if you think they look like domes, all you have to do is spin the moon around. Okay. Spin it and flip the image over, and all of a sudden they'll look like craters again. It's the way the brain works. Okay, so I hope you're enjoying this kind of stuff. It's neat, and like I said, I don't want to risk opening up tonight because the wind out there is still pretty high, and but I will tell you this: we are moving the Sonoran telescope down to Benson, and what we're going to do is move into another building on site. We're not going to try and put it in this building because this telescope is going to have our spectrograph on it, and the spectrograph is going to possibly be mounted to this telescope as another telescope on top of it. All right, and I'll show you where I'm thinking of doing that. Okay, let's bring this out here. Okay, so this is a telescope in the building. Okay, this is our filter wheel. Okay, and the camera is right here. Okay, then right here we have something called an off-axis guider. It's between the telescope and the filter wheel, and what that does is it takes a little tiny piece of the field and finds a guide star in there. So the telescope is guiding literally at its high magnification. And that's why our images end up looking so pretty good, other than wind blowing the telescope around. So that's neat, really neat. So what we're going to do is we're going to mount another telescope on this one. Okay, it'll probably be right here, so it'll be kind of on the side when the telescope is being stowed, and it's going to have a spectrograph system on it. So we'll be able to do things like look at stars, look at other stars, look at other things in the sky like planetary nebulae, and literally decipher exactly what they're made of. Now, this is the next big step, because in astronomy we only have light coming to us from objects, right? Like the moon and stars and so forth. And when we look at the light coming from the stars, we can see different things. One of the things we can see is, of course, the object invisible, the visible spectrum. Okay, But what we can't see unless we use a special device called a spectrograph is the light that is coming from the sun reflecting off of, say, the moon. And then what we see coming back from the moon is a reflection of the sun's light. And we can actually then see dark lines in the spectrum when we break out the light into its components, like we see red, orange, yellow, green, blue, indigo, and violet, right? When we break the light out into its spectrum, we can see dark lines in there. And the dark lines are the lines that we see in the sun. However, those dark lines are called absorption lines. And that's because they come from when the sun's core is the hottest part of the star, right? And that's only about 15 to 20% of the star, and all the rest is along for the ride. But that gas, although extremely hot, is nowhere near the tens of millions of degrees that the core is. So this constitutes, believe it or not, a cooler gas. So when this hot radiation passes through the cooler gas, this cooler gas is absorbing some of that radiation. Hence the sun looks so big in the sky. It doesn't look like a little core with just a gas ball. It looks like a core with all this other stuff around it, this other sun. But that's cooler gas than the core. And so what happens is they absorb, depending on the element that's out there in the outer reaches of the sun, it absorbs energy from the core. And when we look at different elements in the periodic table, which I won't show you tonight, we find that the elements in the periodic table absorb at different locations in that spectrum. And they make a dark line where they pulled a little energy out of that radiation coming from the center of the sun. So we see all these lines, these dark lines. In the sun, it's called the Fraunhofer spectrum, named for the individual that actually discovered the sun's spectrum. And we see calcium, magnesium, potassium. We see all the elements in the periodic table in there. The sun didn't make those. Okay, the sun was made with those. Okay, the sun was made with those. And so if we can look at a spectrum of something, we can figure out, based on those lines, what it's made of. So let's say we point our spectrograph at Neptune. Well, in our visual scope here, it'll look like a little bluish ball. Okay, beautiful. But if I point the spectrograph at it and we look at it, we're going to see methane in the clouds. We're going to see other elements and compounds in the clouds that we can identify. So it gives us that next step into actual science that we can do. And then all that data I will provide to you. So if you want to look at the spectra of Neptune and work with it and play with it, I have a beautiful program that I use from Tom Field. It's called RSpec, RSPEC. And RSpec is probably perhaps hands down one of the better tools that you can use to analyze the spectra of stars. Okay, I talked to Tom the other day, actually. And so what you would do is you would get RSpec. It's literally $24 a year. You can't beat the price. And for that cost, instead of hundreds of dollars a year for another type of spectral product, you can do almost exactly the same things you can do with the more expensive products, and then be able to actually show a stellar spectrum. Okay, and that is one of the cool things that I like to do. Now, let's try. Let me do something here. Let's look at. Let me look at the sun spectrum. Okay. Okay, and let's go to the solar spectrum. All right, and see if we can get image of the Fraunhofer lines, and there they are. Okay, this shows you. All right, this is what a spectrograph would show you. Every one of these lines in the spectrum constitutes a location in the sun spectrum where the hot energy in the core is being absorbed on the way out by different elements. Okay, we have H and K lines from calcium here. They're called. All right, we have, and notice that there's a wavelength under here. This wavelength, okay, is this wavelength is something that we can actually look at and say, hey, where in the spectrum do these lines occur? That's really important, because knowing where the lines occur is really important to understanding what's in the sun and what it's in the star. This is the high resolution spectrum of the sun. We're going to get something kind of like this, and we'll be able to identify a lot of what's in the sun. Now, I know this doesn't look all that exciting like this, but wait until we see a supernova. Wait until we see a nova, a little different. Wait until we see a planetary nebula, and we start looking at what's in there. Then you'll understand what I talk about when I say that, these building blocks of life are made in these objects, okay? When the sun finally dies, all of these elements that we see in that outer envelope are going to be liberated as the star swells into a red giant, and then it goes through a phase called thermal pulse, where it's going to pop up and down, and push these layers off. And as it pushes the layers off, guess what? It's going to end up pushing them out into the interstellar medium. The hot core of the star will become a white dwarf. It'll shrink down really small, about the size of the Earth, okay? And it will then radiate outward with such intensity that it will light up the nebula, the gas, again, just like it, lights up the stuff now, by causing the nuclei in the outer part of the sun to glow. That's plasma. But it's going to ionize the atoms out there, and once it finally pushes them away, and then they'll glow. We'll see hydrogen, which is going to be red. We'll see oxygen, which is going to be teal. Okay? And we'll see other colors in there too. Not very many. It's red, greenish blue, and blue are kind of the colors of the universe. And that's kind of cool. But, for all those colors, you see stars of different colors, right? Except green, and that's a whole nother discussion of something called black body radiation. But we'll go there another day, okay? But this thing right here, this is going to be the spectrum that we are going to be able to capture if we look at the sun. If we look at a planet, okay, then we can actually get a spectrum of the planet. Let's look at the spectrum. I mentioned Neptune, so let's look at Neptune and see if we can grab one for Neptune out there. Yeah, there we go. Okay, so here is a Neptunian spectrum. Let's look at that one. Let's go visit this and see. So there's Neptune. So you see, we'll see. Actually, this is using our spec. It's the product that I was talking about using. Okay, so we can see that we have methane in here. Okay, there's some methane. Now this is using a tool. You can see all these lines, and not all of them have been identified here. Okay, but there are so many lines of absorbed materials. Now, where are we getting this absorption from? Neptune reflects light of the sun. So what's going on? What happens is, what we're actually seeing here is we're seeing a subtle reflection of that spectrum we just saw from the sun, okay? But we're seeing these areas here, an absorption line where there's a dearth of energy coming back. And that is the cloud tops of Neptune are reflecting back the sunlight, but they're absorbing some of its energy. And by doing it, it leaves a little gap in the spectrum being reflected back. This is all sunlight coming back. But these little holes here, these little valleys, are gaps that are caused by the material in the cloud tops of Neptune, which are not letting that energy back out. So we see the sun spectrum and minus the energy that Neptune stole out of it. And so this is the spectrum that we get of Neptune. All right, and so it goes on and on. So this is neat. This is a site called Cloudy Nights. It's actually a really good site. Okay, so obviously we can also look at it differently. We can capture Neptune's spectrum a little bit differently. Using more different tools. But this is stuff that is reserved for real astronomical processing, as opposed to processing for fun, to show you and give you kind of an introduction to the science. Okay, here is another set of lava pits that are collapsed roofs of a lava tube underneath. All right, so when you see these, those usually indicate that, again, on the moon. This again is a simple crater All right, there we are. You see that? And you can see also, let's see if we can find any in here. Sometimes when the moon is struck by things, you'll see boulders that actually roll down the side. Okay, there's one there. It rolled down the side, leaving a path, and it stopped right there. See it? Okay. And sometimes they roll down into the middle, and some they get all the way down. And these are the ones that actually rolled down at some point in the past, but then vibrations and impacts probably filled in their tracks. But pretty cool, you know. And this one is neat because it's sticking up, and it looks like it's a big giant monolith, doesn't it? In fact, it's just a small boulder, but because the light is so low, the shadow gets long, just like you at sunset looking behind you and seeing the long shadow of your body. Well, you're only like 5 or 6 feet tall, right? But your shadow can be huge in length, and it's been used mistakenly to show monoliths on Mars, when in fact all it is what's called raking light, a low angle light, causing a big shadow of a relatively small object. Okay, so that's the reality of that. So neat stuff. This is the moon again. This is the LROC Lunar Reconnaissance Orbiter browser. I have a data point that I'm going to get out of here. That was the Copernicus Traverse that we did. Okay, all right. So that's neat. And that's the moon that's up there now. It's about halfway lit from our perspective. So I hope you guys kind of enjoyed this tonight. This was fun. I'm sorry that we're not getting to open the building tonight. It is, again, it's a risk when it's windy, and it is kind of cloudy. That wouldn't stop me necessarily, because it might be kind of fun to just do. But what stops me is the wind. Wind can destroy a telescope, and it can blow dust and dirt into the telescope, causing severe damage. Look at all the clouds. So it's actually kind of good that there's clouds, okay? Because it won't be the best views. But I just wanted to mention to you also, if you guys will spend time, you can spend time and check us out. Check out our Patreon if you want. Do other things. Go to our store, Etsy store. Many of these things we take photographs of, we put on interesting objects. In fact, I'll show you the Etsy store. Why not? Why not? Just why not? We'll go to Etsy. This is just a quickie, and we're going to go here and go to my account here. And let's go to our profile, go to Sky Tour Shop. Just check it out. This is all stuff. You want a pair of sneakers? I actually have a pair of these sneakers. They're actually kind of cool. They wear well. They're neat. Neato. And by the way, we're a non-profit. These are women's sneakers, so I have the men's. We're a non-profit, so all the money, I don't take a salary. Okay, so all the money goes right into, supporting what we do and giving you something. I also have a program for people that are free members. If you convert to one of our paid members, we send you a Pleiades mug, okay, for doing so. That'd be kind of cool. We want playing cards? We got them. Coasters? We got them. Clock? We got it. Yeah, we have luggage. We have all kinds of things. It's fun, Yeah, so, socks. Yeah, SkyTour Livestream socks. Who knew? We have weekender bags, okay. Dog bandana. I had 2 of these. I had one for my dingo and one for my dog Indy. Okay, so they're really cool. I have this luggage sitting right outside my door here, and I actually take it when I go to Arizona sometimes. That's fun. So anyway, I just thought I'd throw that out to you and show you what we got going on. So again, if you guys are interested, check us out. I really appreciate the folks here. I do want to take questions now, because I know some of you probably have some questions, and I know I've been talking a lot. I just don't shut up. So I'm gonna go back in the chat and see if there's any questions here that need to be addressed. I'd be happy to answer them for you. So I'm gonna go check it out now. And if you have any questions, put them in the chat now. All right. We're gonna start doing Q&As. I also have another last thing to show you here in just a moment, which I will, and that's kind of cool. But ask your questions now if you got them. Let's see. All right. First of all, I didn't say hi to everybody. I got to some of you. Rockstar's with us. Mundus is with us. Mundus Finite, how you doing? And then we have Neurofinusa, Neurofin USA. Oh, hey, cool, man. How are you? Good to see you. Tim F, nice to see you. Karen Belmont, I think I said hi to you. Aurelio, I said hi. Nicola, nice to see you. And I'm going to miss some names, I'm sorry. But Matt is with us. Matt X, nice to see you, brother. And we have more people coming in. We have some new ones here. Alan Drummond is with us. Hey, Alan, how are you? And if you guys haven't subscribed, subscribe to us. I mean, this is kind of a different night. This is our Friday night stream. This is going to happen every Friday night. The only thing that's going to change is the time we do it, because in the summertime, we're going to start later, okay? Because the East Coast time has to be later because the sun won't set until like 9 o'clock Arizona time. So we won't even start probably until maybe 11 p.m. and then do an hour of cool stuff and neato information, and then we'll go into a stream if it's clear. But I will give you any updates on that prior to the stream. But you can count on, for now, moving forward, every Friday night at 9 p.m., Skyder live stream goes live, and we'll have a new set of topics the next time you come in. And let's see now, we have Alan Drummond's in Scotland. Hey, nice to see you, man. I love seeing our international partners come in and say hi. And then we have last reviewer. It says, I just got back from visiting McDonald Observatory. Hey, that's Texas, I believe. That's so cool. I'm reading your messages from way earlier, guys. I'm sorry. Yeah. On the East Coast, the warm part of Scotland. Yeah, that's really good. Lots of golf courses. All right. And now, if you have, let's see. Okay, Oklahoma. All right. I love seeing people come from all over the world. This is good. Time Warp's with us. Thanks for showing us this cool tool. I come in a little late. What is the name of this tool? Well, hopefully you know now, but I'll tell you again. It's actually the Lunar Reconnaissance Orbiter Quick Map. If you look up LRO Quick Map, all one word, okay, you will find it. And you can explore the moon until you're either divorced, late for dinner, miss dinner entirely, forget to eat, pass out, and enjoy. You can zoom and like you can keep zooming in and zooming in, until you get down. Now it goes down to 5 meters per pixel, and right now, look at where we're at now. We're at 0.77 meters per pixel. Look at these. This is the Copernicus crater. Look at the shadows of the rocks at the bottom of this little mini craterlet inside. Actually looks like a hoof print. Okay, so you can see all this stuff. It's just incredible. And we can actually do kind of a measurement too. If we come in here and say, well, I mean, how big is that thing? You can actually kind of figure it out. Well, this right here, it looks like that little rock right there is about, oh gosh, it looks like it's about, it looks like it's about 3 meters. No, 3 meters? Distance. Yeah, it doesn't. It gave it to me when I started it. So like this guy here, for instance, let's go do another one. All right, if we do, say, from right here to right here, 7 meters. So just over 22 feet, maybe or so. Okay, so this rock right here is about 7 meters or so in size. So we're actually closing in really on small objects. So that's pretty cool. So this tool is fantastic for a lot of things, and in fact, it's interesting for way more than what we're doing it tonight for. There's a lot of things that are happening with this tool that it's always being modified. It's always progressing. Okay, and here's something interesting. Notice this impact here. This is a craterlet. Happened after Copernicus, which was what we're in, was made. You come down here and you look. Look at the splash. You can actually see the splash of stuff that came out when this crater was made. You can see also that it hit at an angle right there and splashed this way, splashed that way. See it? See the splashes? You can see them. And then this way. Now, where there's a gap here, where there's no splash, it means that there must have been this outcrop here must have just been shading the area beyond it enough so that the rocks struck and came back down. You can see chronologies of events here when you look at stuff like this. It's really impressive. Yeah, I know. I'm a weird guy. What can I say? But I don't think you really mind. You know? So let's now, let me check out here and see if I've missed anybody's comments here. Let me jump down the bottom. Daryl says there's a new supernova right now. NGC 5907 in Draco. Thanks, Daryl. Thanks, man. Good to see you, by the way. And I'd love to look at that, but unfortunately, the unfortunate news is that it's windy out here, and the clouds are out right now. Look at the objects swinging by, zipping by. They're moving really fast, and we can't take the telescope out when it's so windy out there. It's 26-mile-an-hour winds. So I gotta stop looking at it. I'm just gonna get depressed. So that's cool. Dizzy Lizzie's with us. Hey, Dizzy. Good to see you. And Good Vibes is with us. That's Marla. Hi, Marla. Nice to see you. And Sharon asks, what causes the black areas on the moon? Are you talking about these areas here, or are you talking about, in general, these areas? Because if you are talking about these areas, then I can tell you what those are. These areas are areas where magma deep inside the moon, after large impacts, flooded on top of the moon. You'll notice this looks like a gigantic circle. It is. A large impact struck here. This is called the Imbrium Basin. Mare Imbrium is the name of this location. And if you want to know what things are called, you can come into this once again. Go into the Layers browser and go into Overlays, and then you go to Nomenclature. And then you get all the names, as you can see. Now, there's a lot of them. Okay, so if we zoom in, okay, we zoom in now, and you'll see there's a lot of features. But this is Mare Imbrium, the Imbrium Basin. And you'll notice something interesting. Here is a partial circle. What happened here? Interestingly, this area, this was a crater that had occurred and happened before the Imbrium impact. And then after the Imbrium impact, the lava flooded. It destroyed the wall of the crater here and just flowed in and filled it in with lava from this whole impact area. Okay, who knows how far Mons Pico goes down as a mountain before the Imbrium impact occurred. Okay, whatever it was, it's just outside the Imbrium, just outside the main impact zone. So it might have been created by the Imbrium impact, or it might have actually survived the impact. These are all craters that occurred after the impact because they're sitting on top of this lava. Now notice how smooth this looks. Let's just zoom in for fun. Okay, not looking so smooth anymore now, is it? Let's keep going. Look at that. As close as we get, it's still got many craters going on. Look at this. Look at the tiniest craters we can see. Isn't that amazing? You know, and we're down to like 0.95 meters per pixel. So we're looking at craters that are all under a meter and a half or so in size. The smallest little dots in here are probably about a meter and a half actually in size. So that's amazing to see this kind of detail. You can't hide aliens hiding on the moon with this kind of detail available. Okay. So that's pretty cool. Now we can turn off the nomenclature there. So this is Lunar Reconnaissance Orbiter quick map. So enjoy this, guys. It's pretty cool. And now let's see. Dizzy Lizzy says, how come the moon craters are not very deep? That's actually a very good question. I sort of answered it before, but I think you joined late, and that's okay. I'll answer it again because it's worth saying. Okay. Some of the craters are pretty deep. And the thing is, you don't notice because they filled with lava after the impact. Now let's go back to our 3D globe. And let's do this one thing here. Okay. If we look at, say, these three. Okay, let's look at these three craters. Okay. All right, we have this crater, and this crater. It looks like they're pretty much the same depth. It looks like this and this are the same depth, don't it? With just a ring in between them. Deception is the moon's strong suit. So we're going to come into our tool here, and what I'm going to do now is make a path. And we're going to go from here across to here. All right, and now we're going to see this distance. Now, you look when I come over here, you'll see the yellow ball move along this line. Watch right here. Now look over on the left, see the yellow ball. Okay, the altitude here, the height here, the terrain height here, okay, is literally minus 2,471 meters. So it's below the mean radius of the moon, okay, by 2,741 meters or so. Okay, now we come into here, and now we're in here, and we're down low. This is the lowest spot. Look how much lower this here is. Minus 2491, and this is minus 2761. This is literally 300 meters deeper than this, yet you can't tell. It looks like it's the same depth. And so it goes on the moon. Whenever we see things on the moon like this, we think that they're all the same depth. So this guy then, okay, this right here, we're looking at minus 2759 on average, right to the middle there where it's deepest. Now let's do one over here and go through the middle. This will be more complicated, but we'll go to these in here. We'll go to these outer areas right here. So it's building a profile curve. And so here at this one deep spot, or this one's minus 4,561 meters. And then this area is even more. It's minus 4,567 or 66 meters. Okay, so this bottom is deeper than this bottom by a huge margin. What does that mean? It means that this crater impact probably had more energy than this crater impact. Okay, even though this is bigger. All right, so that's interesting that happened. Now let's do this crater over here. All right, and this is again very telling. If we go to this, go across like this, try to find the deepest spot in this crater. That's right about here. This is minus 4,726. Whoa. So that's interesting because when we looked at this other guy here, okay, the deepest spot on this crater was 4,599. This crater looks like it's shallower, but it's actually way deeper by several hundred meters. Look at that. So this deep spot right here, 4,500, and then we had, what's it right here, is it? 4,600, and it was 4,000, we just passed 4,700. So minus 4,700, meters below the mean radius here. So these craters are all different depths, and that is how it is on the moon everywhere. There is nothing that's the same depth. And I'm going to show you something really interesting too. And this, again, this tool is this guy here, the spanner. Okay, and that's really good. The layers and the spanner, the 3D globe, really cool. Now, one thing we can do is also measure altitudes. So if we come out of here and we go to that Mons Pico we talked about right here, it's like, well, how far is it above the plane? Well, we can do that. Let's do here, and let's go like this. And let's go all the way across the top, across the biggest altitudes, and then back down the other side. Okay, so now we're looking like this. See, we're looking over all of its elevations. And so when we look at it, it's building the elevation map for us. So now we come across and go to the top, and we see we're still not highest, but at the highest point we're at here, okay, look at what it is. The terrain height, minus 634. Okay? Even though we're elevated high, we're still not quite to the moon's mean radius. And the reason is because we're sitting in a vast moon-sized depression of area here, because this massive impact gouged a massive hole, and this, however it ended up sticking up into the above the ground, is still not very deep relative to our crater over here, which is several thousand meters deeper. So interesting how that works. This is elevated this is elevated terrain, but this digs in deep, this digs in deep. So everything's at different depth. Plato, the crater Plato, first of all, besides being 60 miles across or so, okay, if we look at its profile, let's go from the outside through the middle to here. This will be kind of, grungy on the outside because you can have all kinds of spiky stuff. But look at this. Plato's interesting. Here's Plato. But what we're seeing is that it's lower at one end, okay? It's minus 2,567 meters below the mean radius of the moon, which is 1,737. And this is minus 2,300. So between this one, okay, 2,500, and this one, it's 200 meters higher at this end. Now wait. You said these find their exact level. They do. But for some reason, this part of Plato is lower than this part, which at 60 miles across means that this is due to probably multiple leaching out of lava from onto the surface here. And so this one was probably earlier, this one was probably later, so it's a little higher. And if we zoom in, we can start to see some interesting patterning on the surface that indicates maybe different lava flows or somehow caused this, and that this is probably more ancient than this side, perhaps. So there's all kinds of things. And of course, Plato looks like a fun place to land. You'd have, if you got into the middle of Plato, this is what you'd see. Let's go down there. Let me get rid of this right here. All right. And get rid of my unnamed path from before. So if we got into the middle of Plato, this is what we'd see. Okay, we would see, let me get out of it. We'd see this really cool rim all the way around us. Like that. So that's what it looks like from inside Plato. Not very exciting, but if we pull out to the resolution of the Lunar Reconnaissance Orbiter imagery, we can see that, again, craters upon craters upon craters upon craters all the way through. Here you can actually see the bands of the Lunar Reconnaissance Orbiter pass, which is kind of cool. So it's taking really high-res shots of the moon. And so that's interesting. So now we've talked about science all night long so far, but I want to leave you with something else. And that is, objects that I can't explain. Okay, and this is one of the installments in that approach that I want to bring to your attention. And that is, I'm going to bring it up here. Let's see. I'm looking for it now. I have it here. This may be the one. Okay. Okay. So here, first of all, let me start like this. You'll see there are satellites passing through the sky. Every quick thing you see moving through the sky. This is an exposure that right now, this is a 15-second exposure. You can see that in the upper left. This is our all-sky cam. This will be in Benson soon. And if you look, as things move, you see satellites moving all through the sky. And what was that? Did you see that? Let's go back. Okay, here's the Milky Way, the summer Milky Way rising. This is taken back on July 1st of 2024. Another satellite moved through the sky. And then we have that. Okay, that was weird. I don't know what that was. Now watch this. It curves. Now, I happen to know that even though I said, is it a rocket launch or is it a UAP? I'm going to say this. I actually don't know what this was. Now, when I captured it, I did a couple things to try and determine what I was looking at. All right, and let me go back. Let me go back to this object. Here it is. Okay. All right. So you're seeing this object now. This is what we're seeing, and now, as the sun set, once again, you see the stars, and at sunset you basically see more satellites than before. So that's the best way to see them, is just after sunset and just before sunrise. But if they're far enough up in the sky, you can see them at night too, way in the middle of the night. We photographed satellites at midnight, but they're really, really, really so far out that they don't go into the terminator of the Earth. They actually are visible. So everything you just saw, those are satellites buzzing through the sky. Okay, and then you'll see this thing again. Now, I'm going to tell you what I did to analyze this. Okay, so first of all, here it comes. Okay, there it is right there. It's very bright. It's illuminated by the setting sun. Okay, notice the direction, west. That's west. Okay, and then as it comes in, right, it's bright, it's bright, it's bright, right, and then it curves. There's a satellite there, and it has a line next to it, and we're going to talk about that line in just a minute. Now, it starts to curve. Okay, this is a curve that you can't explain by a satellite. Okay, and that curve is strange because it looks like it goes along with this object, doesn't it? And that's kind of what we're looking at there, right? So then let's keep going, and you'll notice that that guy fades out, and notice how it's going bright and then it's fading away. Well, that's exactly what the satellites were doing. They're fading. Okay, so the question is, what is this? And then, of course, the thing that really makes this mysterious is that, yes, these are satellites. Again, this is a 15-second exposure. So this was a point of light moving through the sky, and it took 15 seconds to go there. And then it proceeded to make this strange gyration. It went like this. It came in from here, turned this way, and then went back that way. Watch. Look at that. All right. So now, what we're looking at here is we're looking at something that is absolutely unexplainable. I thought, was it a military aircraft? And of course, no. And the reason is because of the way it fades out. It was brightly lit by the setting sun over here, okay, which is 8:57 in July. The sun was basically, still bright enough to light it up very brightly. Yet it made that curve, and that curve is completely unexplainable. Now, I'm MUFON's, the Mutual UFO Network's chief photo and video analyst. I run the photo analysis team for MUFON. I can't tell you what this was, and that makes my job very exciting. Okay, I can't tell you what this was. All right, so that's our mystery for tonight. Okay, now I want to show you one more time this guy. Okay, see that as it moved away. All right, as it moved away, and this is slow motion, right? We see that one there, okay, but watch now. Now we see that. That's the line that was bright before, now getting fainter, but now watch. Now this one shows up, and it's moving as fast as this is. Okay, and then we do this, and now they're moving together, and there's a third one. What are these, and how did they change direction so quickly, right? And there's another one there. I do not know what that was. It doesn't match aircraft of any kind. So I don't know. I do not know. Spock, I don't know what it was. Fascinating, Captain. So clearly, I don't know. And Bob, C&D Boy, says, that was wild. Mark, what do you think? I don't know. I don't know. I really don't know. So was it an actual UAP? Maybe. Oh, and by the way, I got to tell you, it's not confirmed yet, but I think I'm going to be on a UAP task force, where we're going to analyze data to study UAP, and this is at the government level. It's not U.S. government; it's state government, and the U.S. representative who put this bill together and who got the bill passed, a guy named Joe Hoxa. The Joe Hoxa actually got the bill passed to actually study UAP, and he did that before he knew who I was. And then when he found out who I was, he immediately wanted to have lunch with me. And so we had lunch, and he says, you know, I want you on the team. You know, it goes without saying you're on this team. So there's going to be a school of engineering involved. I mean, this is a real crazy time, because people are taking UAP very seriously. And after that video you just saw, all I can say is, what was that? Right? What was that? Come on, you don't. I don't know. You don't. I don't. Yeah, I don't know. You don't know either. And don't pretend. So that's actually pretty cool. Joe Gabori, Gabori or Gabori, okay, says, I saw a strange craft tonight. Okay, and Joe says, I just joined, but my daughter. I just don't know what that means. JSO, how you doing? Kathy Messick's with us. And again, I'm sorry for some of the people I haven't seen. James Small said, hey, Mark, say hey to a friend of mine, Braxton. He's 16, loves astronomy. I introduced him to your channel tonight. Hey, Braxton, what's up, man? Welcome. I hope you're still listening. Yeah, unfortunately, you're not seeing the observatory tonight, Braxton. I mean, this is it. I mean, we would normally have this open, but it's really kind of windy. So I can't open it and show it to you. And this is actually 2,600 miles from me. I'm in Connecticut, down here, and this is out in Arizona on a high plateau at 3,500 feet. So we have some really interesting stuff here. Okay. Dizzy, I'm going to answer that for you. Very good question. So we can't open tonight because of the wind out there. Now, the wind's supposed to calm down, but I can't take the chance that it's going to continue. All right, so I always err on the side of caution no matter what the case, and I don't ever get pressured to open it when it's windy out. I open when I shouldn't many times as well. Like when there's thunderstorms coming, I'll still open for a little while. And if anything gets stuck, I got to make an emergency call to someone out there to go out there and, fix whatever could be wrong. But and this has been a very reliable system, so I'm very, very pleased with it. Coming back now, let's see. Dizzy said, the dark side of the moon also mapped out. I'm glad you asked that, and I didn't spend too much time there, but let's back out here, because we are looking at the near side of the moon a lot, and this is where we're looking here. Okay, and if you notice that there's Plato, okay, this is kind of the side we see right about here, right? But can we spin around? Oh yes. And I want you to notice something. Look at the dark side, or I say the far side. There is no dark side. As Pink Floyd says, there is no dark side of the moon, really. As a matter of fact, it's all dark. Not true, of course, but hey. Now, the moon, this side of the moon is actually fascinating for one other reason. And that is that this here is the lowest spot on the moon. It's called the Aitken Basin. Okay? All right, the Aitken Basin is the lowest spot on the moon. The highest spot of the moon is up north just a little bit. Okay, and that's because when this impact occurred, a massive object was buried deep underground here, and it's actually seen with instrumentation. There's a giant object underneath the moon here, possibly the remnants of an asteroid that struck at a relatively slow speed. Relatively, still fast but slow for that. And and so this is that spot. Now I want you to notice something too. When you look here, where's all the seas? Where's all the dark side? Where's all the dark stuff that we see? Right? Where's all this? Why is this? Why is this here? Why is this lava on this side, and why is there none on this side? I mean, you have a couple spots. This is Mare Moscoviense right here, okay, and we have Tsiolkovsky crater right here, okay, which is kind of cool to look at because you zoom in on it, and check this out. It just gets better and better and better, and we can go to the peak of this mountain in here and look at the detail we see in this. Look at this. Talk about a detailed view. And this is in 3D, so we can actually, say, whoa, that's a long ride down on a sled. That'd be kind of fun. But the moon dust is like glass, and you'd probably be all sliced up by the time you got to the bottom. But one of the things we do see is tracks from boulders that have rolled down. Okay, that's what we see on these large crater walls like this. Okay, and that's really cool. But backing out now and coming back to answer your question, Dizzy, you asked about the dark side. I'm sorry, the far side of the moon, and was it mapped out? And the answer is yes, absolutely. Okay, now let's move this up a little bit. Now, there it is. It is mapped out. Okay, and if we go back to the near side, okay, this is our near side right there. Okay, we go to and notice all those Maria, those areas. Why did lava come spewing out from large impacts? We had an impact here, we had an impact there, an impact here, okay, and there. Why here? Why do we get impacts showing that? But on the far side, we don't see but like one or two, and that's all. What's different about the far side from the near side? And if you're interested, I will tell you. Okay? And so what's going on the far side, as you can imagine, there's the Earth. See it? Okay? What's interesting is this side of the moon, remember, billions of years ago, and after the moon was tidally locked to the Earth, the near side of the moon was a lot closer to the Earth. And at the time, there was a bombardment era called the late bombardment era, early bombardment era as well. And this planet, ours, was actually molten for a good deal of time. And the moon curing and cooling a little, curing a little bit and cooling. What happened was when meteors struck the Earth, and millions of them did, just like on the moon, material rose up in the space around the Earth, and a lot of infrared energy from that molten Earth was radiating toward this moon here, radiating toward the moon. Now, radiation has a pressure associated with it, okay? And that this is a good position to be in. The Earth is that way, okay? So radiation pressure was pushing material that was hitting the moon up into the space around the moon and pushing it past the side here onto the dark side where it accumulated over time. Okay? So that meant that the front side of the moon facing us has a crust that's thinner than the far side. The far side of the moon's crust is much thicker. So meteors striking there left what should have been the front side view. Lots and lots of craters with highlands, highland areas, okay, here. But in fact, when we look on this side, we notice that impacts on this side, which were just as numerous as on the far side, could punch through that thin crust to the molten moon still waiting below. And that stuff could flood out on the surface. That's the idea, that's the theory, that's the thought process one of them anyway, about how this actually happened and why the moon near side has all these marias, because it's thinner. And in fact, we do know that when we look at the moon, okay, this side of the moon is thicker and larger than this side of the moon. The moon is oblate, and this is an exaggeration, but it looks more oblong mass-wise. So the center of mass of the moon is actually probably a little farther toward the back of the center here, okay? But because the moon is locked tidally, it doesn't just flip around. Now, if the moon got hit by something, maybe it could, but it's been tidally locked for billions of years. Isn't that cool? I think that's pretty cool. You know. All right, Donald Kunzer says, all the impacts coming from outside coming at us. Did you ask a previous... let's see. Okay. Sharon says, granddaughter's 14, and on Fridays, we put on our Sky Tour t-shirts and watch it together. Oh, it's so cool. That's really cool, Sharon. I really like that. Hey, Sam S., welcome. Let's see. And I'm just looking for more questions if you guys have. I'm sorry if I'm missing questions, guys. This is, this is the first Friday night, permanent Friday night stream that we're doing. So I'm hoping that this is all pretty cool. Asher, hi Ash. Asher's with us. Nice to see you, man. And Dizzy Lizzie, hopefully you enjoyed that explanation. It looks like maybe you did. Yeah, and so really cool stuff. Good vibes. Cool. Yeah. So this kind of gives you an idea about the genesis of our moon. It's not a perfect set of theories, but it's among the theories we have, that this side was thinner and could be punched through easier. Now, we see the moon after the fact. We see it after the Earth and the moon were molten, after they cooled, after the Earth's infrared energy pushed material, and then after the moon spiraled away to 240,000 plus miles away. We're seeing it after the fact. So what does that mean? It means that this is our snapshot of what actually happened in the universe. All right? It doesn't. Now, if the moon started this far away, it most certainly wouldn't look like this. It most certainly wouldn't look like this. This all happened when it was much closer to that blue marble over there. Much closer to that blue marble. Earth was really big in its sky when this process occurred. All right, tidal locking it and causing it to be lopsided in its mass. Okay, so that's what we see now. And there's a lot of moon theories I've dealt with over time. Dealt with a lot of conspiracies. The moon's hollow. Okay, aliens live on the far side of the moon. Well, the far side of the moon is mapped really detailed, and you can zoom right in the same way you can zoom in on the front side. And I can tell you that any of this, and isn't this crazy? Look at the detailing. Look at the moon mountain shadows. Isn't that cool? That's actually a cool photo. You're actually looking at the shadow of the central peak of this crater. Look at that. That is neat stuff. Okay? And so we're seeing this very turbulent area here, right? And the Lunar Reconnaissance Orbiter could probably pick it out pretty easily, And as data comes in, you see it fills in good data with good data. This is an extremely turbulent location on the moon, but this peak is not pointy like that. That's again low angle light. Here is what it actually looks like. Look at that. See that? Isn't that cool? So you can see how it actually looks, and that is actually the shadow of that moon mountain, basically. It's not a very sharp pointed peak, but it does have this depression at the top. Isn't that something? Now, there are moon volcanoes that are long, long extinct. And this, on the other hand, you can see this is actually a crater. This was not a moon volcano, but it has... Now, as we get closer, by the way, you also see different data sets. We pull out, and now we see different data sets, okay, with lighting differently. And as we get closer, well, we see the more I guess, detailed data sets. And that's kind of neat, you know. So again, neat stuff. And again, we're in the 3D globe view of the moon. And, you know, it's really neat to actually, you know, travel across the moon like this while we're looking at it. You know, we can go faster too, like this. All right, stop where we want. Look at different aspects of the moon. See our shadows. Move to the other shadows and see those shadows from this mountain right here. So it's really cool. And then look at, like, close right in. Again, we're looking on the far side of the moon, guys. Okay? And that is by far one of the most exciting things. Like I said, you know, you lose your marriage, you forget to eat dinner, you drop 10 pounds because you just spend time looking at the moon. And by the way, I did another thing too I wanted to share with you. I see your question, Michael. I'll get to you in a second. Hey, Star Marshal, how you doing? So one of the things that I also did on the moon was when the lunar missions occurred and the Apollos were done, the ascent stage of the lunar module went back to the command module, you know, the pointy guy, and they attached, the astronauts transferred in, they disconnected this, and they let it go down into a low spiraling lunar orbit till it crashed onto the moon. Well, guess what? I've located those locations where they crashed, and you actually see the splash of debris, because that was, now remember, that was like a balloon with air pressure in it. Okay, the moon has no pressure, so it's always pushing out, and its structure held it together like an airplane fuselage at high altitude. So when you pop that, it just explodes and the debris goes everywhere. And that's what I caught in various spots for the different lunar missions. You can actually see the splash hitting the peak of a mountain and then going beyond it and littering debris beyond it. It's so cool. And maybe I'll do a stream on that at some point too, so you can see all the crashed lunar modules. There's a lot of other places on the moon you can see too that we haven't looked at tonight. Like when they took the LEM out of the stage that was in that other stage of the rocket, that stage was allowed to fall to the moon and crash, and it crashed, crumpled it, and made itself a little crater. Okay, and that was interesting in and of itself as well. So there's a lot of cool stuff. All right, so Michael says, I could probably ask 2 hours of questions just on the moon. This is awesome. I do have one question. When you can you ever process the all-sky unidentified images you showed? Actually, the all-sky camera resolution is what it is. So maybe I can do that. Maybe I can process a little better. But by adding some of the things I do, we might lose some of that detail as well. So, you know, that's kind of tough. Let's go here now and just see what we're looking at. Let's refresh. It'll be night here. Yeah, so we can barely even see some of the stars because the moon is at first quarter. We don't care. I mean, but if you notice there, we got we still got wind out there. I'd love to show you some things, but we can't. I keep punishing myself. All right, so that's cool. So tonight we checked out the moon. We looked at the Lunar Reconnaissance Orbiter. We actually did some interesting Photoshop work. We actually did some analysis and processing of some of the galaxy images we did. Really, really interesting stuff. I showed you the cool anomaly that flew through the sky on the all-sky camera there. And this is just the beginning, guys. Our Friday night streams will encompass this plus actual live streams moving forward. And don't forget that during the week, this isn't the only time we'll stream. We will have bonus streams where during the week we will also open the telescope if it's clear and we have an opportunity. But Friday night, you can count on Friday nights. And as we move toward the summer, we'll start a little bit later. And what we'll do is we will end up streaming. Tonight, I'm doing this cloudy night stream because we don't have the ability to open the telescope tonight because of the wind. Right? If we did that, you wouldn't have seen any of this. You would have just seen all stream. And of course, one mysterious object. I've got more. Don't worry. Stick around. You'll see more, but not tonight. That'll be next time. So I want to make sure that you guys like what we're doing. If you like this idea of a permanent stream, let me know. Please comment, like, and subscribe. You know the whole deal. But we need that. We really, 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 really need you to tell us that you like this. Give us a thumbs up and subscribe to it. It's, you know how it is. It's free. Join free if you want. And join as a free Patreon member too. There's no charge, but you get shout outs and stuff like that. So I would love to see you do that and love to see you be part of this. I enjoy all of you guys. We're going to call it for now, but I want to thank you for coming out to our cloudy night stream. And I will torture myself just once more. Yeah. I hate the wind. So there we go. But anyway, guys, I hope you guys have a really good evening. If you're interested, if you become a Patreon member, you become a paid Patreon member, our music album Rising is available to you for free. We'll give that to you. So I'd love to have you listen to our music, our moon music. Kind of cool. Yeah. Thanks, Mike. Like. Yeah. So let me know what you want to do. If you like this stuff, we'll do more. This particular application is available. And the next time, if we do it again, what I will show you is how to actually 3D print some of these and show you samples of the ones I've done. Okay? And if you want, you can also buy those from us because we sell them. And if you have a favorite crater on the moon, I can literally get any crater in high resolution that you like on the moon. Most likely it'll be on the front side. Most likely it'll be Plato, Copernicus, Aristarchus, okay, or Tycho down here, Tycho right here, okay. Very, very cool crater indeed. Remember, TMA1 was in here. What's that? If you don't know, you'll have to wait till the next time. Look at that. Zoom right into the peak of Tycho. Look at that. Wow. Now that is an area where a lot of damage occurred. That is the bloop. That's the, from the water. And it was just actually not water, but rock that was liquefied in the process of collision. And then it froze as it went back bloop, to the middle. And the rest was lava infill that flooded up. So you guys, you know what? I'm probably going to leave this open and hang out a little more. Just doing it myself. But I'm going to close the stream because otherwise I'm going to keep talking and I'll lose my voice. I have to be up early tomorrow. I got to head out to do some things. But you know something? I wanted to do the Friday night stream with you again, first of many. And the only thing that will change is the time and the content. All right? The time will change from 9 o'clock to a little bit later as we get into the summer because we have to, because it doesn't get dark in Arizona until much later. We can start earlier and do an hour of this kind of stuff and then do the stream. So I'll probably start an hour before we're ready to stream. And then we'll just move into the stream and go from there. I think that's pretty cool. I like that idea. So guys, thank you so much. I hope you enjoyed this, and we will be back next time. I'm looking so forward to showing you more. Boy, I got more UFO things to show you too, which are really cool. So next stream, you'll see some of that. All right, guys. You guys have an excellent evening. I know I have had a great time with all of you. Thanks for joining, and until next time, keep looking up. See you guys.
Stars so bright in the sky, on Arizona nights they fly. Nebulae in colors rare, galaxies beyond compare. Sky tour in the night so clear, brings the universe near. Realtime wonders to see, streaming live for you and me. Lift your eyes to the skies, universe in all its light. Sky tours bringing the views. Every night feels brand new. In the dark, the night unfolds, stories of the cosmos told. Through the lens, a distant dream, living real like a gleam. Far away, up so high, across the stars beyond the skull. Through the lens, a distant dream, living real like a gleam. Lift your eye up so high, across the stars beyond the sky. Sky tour shows us the way, every night a new display. Lift your eyes to the skies, universe in all its light. Sky tours bringing the views. Every night feels brand new. Lift your eyes to the skies, universe in all its light. Sky tours bringing the views. Every night feels brand